Okay, this would be about a 15-minute question. It involves some moving particles and some Riemann sums at the beginning here. So let's pause the video here, read through it, and like I say, sharpen the axe. Pick out what we're going to need to do before we just dive right in. All right, so we have a particle moving in a straight line. We have our nice grid given to us. We're going to use in part A midpoints of rectangles to find the approximate value. So we're going to find the area here. That's what we're doing. In part B, we want the average velocity. Well, average velocity is really distance over time. So this area that we just found here is in fact the distance that we've traveled, or the displacement here. And we're going to find the average acceleration. So acceleration is going to be slope. So we want the average slope, and then we're going to find this approximate slope at time equal to 6. And then our last question, what intervals of time is the acceleration negative? So we're going to have to analyze the numbers up here to get those accelerations. All right, let's look at each one of these individually then. Okay, so we're going to start with 5 midpoints. You notice we go from 0 to 30 all the way here, and that is going to split up nicely into 5 equal lengths. So if we go 6, 12, 18, 24, and then 30, there's our 5 equal lengths, and we're using the midpoint as the height. So there is the middle, and the middle of that rectangle. So we're using the middle of each of these rectangles to be our height. So let's set this up. Our integral from 0 to 30 of Vt dt is 5 rectangles. Well, this width is 6 and the height is 7.5. Okay, and then we have our next one, width of 6 and 12. The next rectangle, 6 times 13.5 is that midpoint height. 6 and 14, and finally our last rectangle here is 6 and 13. All right, so this just becomes a calculator question, so I'm going to keep my timing here, but I am going to punch this into my calculator. 6 times 7.5, 6 times 12, 6 times 13.5, 6 times 14, plus 6 times 13. And I got 360. Let's use appropriate units. That is going to be meters. All right, in the next section, we're going to use that result from part A and find the average velocity. Well, just calculus-wise, remember our average b minus a of our integral. That was our average of a function. So we're going to get 30 minus 0 of our integral 0 to 30 Vt dt. So that actually works out to our 360 meters that we just found divided by our 30 seconds. And if we do all of that, again, punch it into my calculator, we can maybe do this. In fact, I probably don't even need my calculator here. That is going to be 12 meters per second. So there's my average velocity. So we're actually making some pretty good time here. Okay, let's look at these last three kind of as a group. We want average acceleration. Okay, so we don't have the equation. So it's not like we can actually find the equation for acceleration. We can't take that derivative of velocity. We don't know what it is. But it is just slope. The average acceleration is the average slope of this curve. So we can see this curve is kind of going up, and now it starts to come down. We're not going to sketch it out or anything, but we want the slope from the start to the end. So slope, remember, is just rise over run. So we're looking at y2, y1, x2, x1. So for us, that means acceleration, or our average acceleration, is going to be 12.2 minus 0 all over 30 minus 0. I'm going to punch that into my calculator. 12.2 divided by 30, and my average acceleration is 0.407 meters per second squared. There's my average acceleration. Okay. Okay, let's try the last two parts. Let's see if I can fit them on the same page. So we're going to find the approximate acceleration at 6. Again, we can't find the derivative of velocity. But when we want to find the approximate value of something, as we can think of it like a tangent line. And we're going to make 6 the middle of our tangent. We're going to make this 6 the middle. So we can take any interval here where 6 is in the middle of our interval. So from 3 to 9, we could even use 0 to 12 if we wanted to get an approximate value. So we got a couple of choices here. But again, we're looking at slope. y2 minus y1, x2 minus x1. So for this particular interval, I'm going to use the 3 and the 9. I'm going from, 12 is where we end up, right? 12 minus 7.5 and 9 minus 3. That puts 6 in the middle. That's going to give us the approximate acceleration. The approximate slope at 6 is the slope between 3 and 9, where 6 is the middle. All right, let's punch this into my calculator now. So I'm taking 12 minus 7.5, and that's 4.5, and I'm going to divide that by 6, and the approximate acceleration at 6 is 0.75 meters per second squared. Last part of this one, during what intervals of time is the acceleration negative? Acceleration is slope, and if we look at this, we can kind of see, like I said before, we're increasing all the way to 18 seconds. We're increasing. After 18 seconds, our graph starts to decrease. So a quick little sketch of velocity time. We are increasing up to 14 seconds, and we're up to 18 seconds, and we're decreasing. Our velocities are coming down after 18 seconds. So when do we have negative acceleration? Well, it looks like negative acceleration from 18 after 18 to 30. So that looks like our interval of time. And we're done with this question.